What we want to do for a good chunk of time today is explore distributions of sums of random variables. In other words, I've got two random variables, say. Let's keep it simple. Let's keep it at two random variables, x and y. And I add them. What kind of random variable do I get? Let x and y be two random variables. Are they discrete? Are they continuous? Are they mixed? I'm not saying at the moment. Two random variables. Saying that these are random variables, as always, means they have distributions. If they're discrete, they have probability mass functions, PMFs. If they're continuous, they have probability density functions, PDFs. What if they're mixed? Can you mix? Yes, I mentioned that before. There are mixed random variables that are somehow both discrete and continuous. We never really delved into that because it's kind of hard. Let S be their sum. S equal x plus y. The question is, what is the distribution of S? I hope it makes some sense that if x and y are discrete, then S should be discrete. If x and y are continuous, then S should be continuous. If x is discrete and y is continuous, would S be mixed? Maybe. Probably. Is there anything else we need to assume? Possibly. Well, let's go ahead and do the continuous case. We will assume x and y have particular distributions here in a minute, but not quite yet. We can use the CDF method. So I've emphasized the CDF method a few times here. CDF method is not something in the book. They use something called the transformation method at the end of chapter 4 to figure out distributions of transformed random variables or sums, perhaps. I prefer the CDF method. And so I've shown you that a few times, and I mentioned it in an email yesterday. The CDF method is to first find the CDF of the new random variable and then differentiate it in the continuous case to find the PDF. That's the method. Capital F sub capital S, say, of little s. How could I make it a little s? Should I make it cursive? I'll just try to make it a smaller s. So there's a small s. This is a big S. Maybe I can emphasize that by doing that. Maybe I should do that. This is a capital S. It's a random variable. And its variable is a little s. As always, the CDF, whether the random variable is discrete or continuous, is the probability that the random variable is less than or equal to the given number. This is a function of the given number that's an ordinary kind of variable, little s in this case. It's always this. That's always the CDF, whether it's discrete, continuous, or mixed. The way you calculate it depends on whether it's discrete, continuous, or mixed. So how are we going to calculate this here? Well, what is S? S is x plus y. So I got to figure out the probability that x plus y is less than or equal to S. How in the world can you possibly do that? Well, you relate it to chapter 5. X and y, you need to assume they have a certain joint distribution. So here's where the assumptions start to come in. You could draw an XY plane. And the condition that x plus y is less than or equal to S could be thought of as a subset in this XY plane. What subset? Think about the equation little x plus little y equals S. That's equivalent to y equals negative x plus S, which in this plane, if you think of x and y as being ordinary variables, nothing about probability here, is a line with a slope of -1 and a y-intercept of S, right? What's S? I'm not saying. Pretend S is right here. This equation defines a line with a slope of -1 and a y-intercept of s, it would be a line like this. And since the y-intercept is s and the slope is -1, the x-intercept turns out to be s as well. Think about it. You can see when x is 0, y is s. You can also see that if you plug in x equals s here, you get -s plus s is 0, y is 0. And this inequality then would define all points in the plane below this line, wouldn't it? Everything down here. So if we knew the joint distribution of x and y, we knew the joint PDF, we could integrate it over this infinite region to find this probability. Doesn't sound so easy. But how do you know the joint PDF? Assumptions. Assume you know it. How? Well, you could just make something up. Although if you were given x and y, if you made something up randomly, it probably wouldn't work. Because probably the marginal PDFs would not match the PDFs of x and y. You can't just make something up randomly, unless you're very smart, to make the marginal distributions match the distributions of the given x and y. The simplest thing to do, almost always what we do, in fact, is assume x and y are independent. That thing makes things a lot easier. We assume, key assumption, assume x and y are independent. What does that do for us? It makes the PDF, for the joint PDF, trivial to find. And the marginal PDFs will be correct. Why? Because it implies the joint PDF is going to be the product of the marginal PDFs. And if you know the PDFs of x and y to begin with, what this means is you just multiply them to find the joint PDF. I.e., you've never known I.e. is Latin abbreviation for, in other words, id est, I think it means. I.e., the product of the PDFs of x and y define the joint PDF. This equation right there is the definition of independence. A bivariate random variable x and y will have x and y being independent random variables if and only if the joint PDF is the product of the marginal PDFs. That's a definition. Effectively, what I'm doing here is I'm using this definition to create a joint distribution where x and y are independent, for the purposes of figuring out the distribution of s. That's why we're doing this. Because I can integrate this product. And integrating this product turns out to be relatively easy, even in the abstract, because this implies that if you do a double integral of the product, the double integral of the joint PDF, let's just keep it simple here over a rectangle, say. Let's say dy dx, where x goes from a to b and y goes from c to d. If this is the product of two functions, one being a function of x and one being a function of y, maybe I should justify what I'm about to say. Let me go ahead and justify it here. When you do the inner integral with respect to y, the inner integral with respect to y, you're treating the x as a constant. And that means that this thing effectively is thought of as a constant for the inner integral and can be brought outside that integral. It's a constant with respect to the inner integral. And so you can write the following strange looking expression: the integral from a to b of f sub x of x times the integral from c to d, which I'm going to make a little smaller, of s sub y of y dy dx. And this thing now, with respect to this integral, is a number. This is a constant. And it really is a constant, even though y is a variable, because I'm integrating a function of y with respect to y over a fixed interval. That is a constant. That's a number. That whole thing can be brought out in front. And so what we end up with here is the product of two integrals. The integral of fy of y times the integral of fx of x. Almost out of paper here. And that's a very good thing, right? That means this double integral could be done this way, and that should seem good. Probabilities for the joint random variable can be found as products of probabilities for the individual random variables. That should seem good, and it is. So again, I'm assuming x and y are independent. That means the joint PDF is the product of the given PDFs. That means this is true, and it's going to mean I can figure out ultimately this more easily, though it still is tricky. Let's do it for a couple particular examples now. Okay. Let's start by assuming x and y are both exponential random variables with a mean of 1, say. So this is an example now, example 1. Assume x and y are independent exponential random variables with mean 1. They both have the same mean of 1. They're both really the same random variable. But wait a minute, if they're the same random variable, shouldn't we call them both x or both y? No, you don't want to do that. Why not? Because we want to imagine that even though they're modeling the same situation, their observed values could be different. In a given experimental situation, okay, say in the discrete situation, me shooting free throws, I shoot 10 free throws one time and I make 4. I do it another time, I make 3. The observed value of x is the outcome of my first trial of 10 attempts, y is the outcome of my number of successes for my second trial of 10 attempts. They have the same distribution, binomial, n equals 10, p equals 0.4, say, but their observed values in that particular example are different. I mean, they could have been the same, but they also could be different. So we want to use still different symbols for them. S is still their sum again. S is x plus y. Once again, we're trying to use the CDF method to find the distribution of S. It is still this probability, which is still this probability. But now to compute this, I need to now do some integrals. I need the joint PDF of x and y based on knowing their marginal PDFs. Well, they're exponential with mean 1, so I could say little f sub x of little x is e to the negative x. And I could say little f sub y of y is e to the negative y. And at least if I'm going to use these PDFs instead of CDFs, I need to do integrals. Now you might wonder, could I avoid integrals by using CDFs? Maybe, but let's do with some integrals here. It'll be a little simpler than the general case because I only need to worry about the first quadrant, because exponential random variables have have PDFs that are 0 when the input is negative. These equations are only when X is positive and Y is positive. Yeah, they are the same formula, but it is worthwhile using different letters. So I only have to think about the first quadrant. I only have to think about positive values of little s. Once again, I have to integrate over this line, over the region that's under this line, but in the first quadrant, I can integrate over this triangle. What will the integral be? And yeah, here it's tricky. It's tricky to think about it this way here. I think it is best to actually do the integrals and try, instead of trying to think about it as a product. We're actually going to do the double integral by doing it as an iterated integral. Here's X, here's Y. I'll do it with respect to Y first for the inside and X on the outside. That's how I typically do it. X is going to go between two numbers, two fixed numbers. And when you look at this picture, you want to think of S as fixed. So X is going to go from 0 to S. Y, for any given X, goes from the second coordinate of this point to the second coordinate of that point. This point has coordinates x0, its second coordinate is 0. This point has coordinates x comma s minus x. Right? Because that line is the equation y equals s minus x, slope of -1, y-intercept of s. I wrote it as negative x plus s before. Y goes from 0 to s minus x. Of the joint PDF, which will be the product of these two, I'm integrating with respect to y first, then with respect to x. I could combine these two things into one integrand like this, or like this. That's okay to do. Is it worthwhile to do? Yeah, I suppose that's probably worthwhile to do. That's a property of exponents. So integrate with respect to y first, treat the x like a constant. Antiderivative of this, you'll get an extra factor of -1 in front. Y goes from 0 to s minus x. And then that thing will ultimately depend on x and be integrated with respect to x. Remember, s is thought of as a constant. When you do the integral in the end, s will be a variable, but while you do the integral, think of s as a constant. So plug in the top number, s minus x, in place of y. If you plug it in place of y, you get negative x minus the quantity s minus x. That's negative x minus s plus x. The x's are going to cancel. You'll just be left with a minus s, right? Minus s. Then subtract what you get when you plug in y equals 0. You get that. I think that's right. Try checking it. Double check. Well, plug in y equals s minus x there. The x's do cancel because of the minus sign going through. Negative s. Yep. Okay. Plug in y equals 0. Yeah, I think this is right. Here, the two minuses make a plus. We're integrating this constant times this function of x dx. S is a constant. We're going to get negative e to the negative s times x. That's just a number. Integrate it with respect to x, you get that number times x. Integrate this one, you get another minus sign. Now x goes from 0 to s. So we get negative, I'll put the s in front, negative s e to the negative s minus e to the negative s minus, plug in 0 for x, 0 minus e to the negative 0. This all becomes a +1 there. Looks like the CDF of the sum is this. Never seen a CDF like that before. I've not made a mistake. This is capital F sub capital S of S. Not done. That's the CDF, but we're more interested, typically, for the purposes of finding means and variances, in the PDF. Little f sub capital S of little s is the derivative of capital F sub S of little s. Differentiate this. 0 minus, okay, I got to use the product rule there. Left d right plus right d left. That was the product rule there. Then differentiate negative e to the negative s to get a plus e to the negative s. I do get some cancellation. This cancels with this when you distribute the minus sign through. It all simplifies to the negative signs that cancel s e to the negative s. That's a fairly simple PDF. Since x and y have to be positive, s has to be positive as well for this formula to be valid. Is it a PDF? Does it integrate to 1? You could do it by hand. It wouldn't be too hard. You'd want to use integration by parts, a fairly simple integration by parts. If you didn't know, you can make infinity show up there either with the palette. There's an infinity button somewhere right back here. Or you can do escape, INF escape. S times e to the negative s, don't forget to use a capital E, does integrate to 1. It is a valid PDF. Is it a PDF of a random variable? We know. Somewhere in chapter 4. It's not exponential, right? Because exponentials are 1 over beta, e to the negative x over beta. We have an extra factor of s in there. Or an x if you call the variable x. However, it does turn out to be the PDF of something we know. It's just not obvious. What is that something? Go back to chapter 4. Well, I'm really excited to find out. What is it? What is it? What is it? That maybe? Gamma? The beta would have to be 1. What about the alpha? I had an s in front, s to the first power. Alpha minus 1 would have to be 2, so alpha would have to be, alpha minus 1 would have to be 1, so alpha would have to be 2. Gamma distribution, alpha equal to 2, beta equal to 1. Is that right, Mathematica? Tell me, is it right? I gotta know. Mathematica, PDF, gamma distribution, alpha equal to 2, beta equal to 1. Yeah, match. It's a gamma distribution, not an exponential distribution. Exponentials have alpha equal to 1. Gamma distribution, alpha equal to 2, beta equal to 1, is the distribution of the sum of 2 exponential random variables. What does its PDF look like? What's the graph this look like? Goes up, then goes down. Whereas an exponential distribution just goes down the whole time, decreases the whole time. This one goes up at first before it goes down. It's a little more, just a little bit more normal looking. Bell-shaped looking, well, not quite. It's certainly not symmetric. It's not a normal curve, but it's a little bit closer. I wonder if that's an accident. No. And it's one of the biggest theorems in mathematical statistics that I'm hinting at here. Got a big name. It's called the Central Limit Theorem. That this is hinting at. Central Limit Theorem is a big theorem in chapter 7. Let's do another example. Example 2. We're going to assume x and y are uniform on the interval from 0 to 1 and independent. We're going to let f's be their sum. Let's use the CDF method again. Capital F sub capital S of little s is the probability that capital S is less than or equal to little s. But what is capital S? It's x plus y. Here's the part where I made a mistake in my drawing. Make a drawing. We're once again thinking about regions underneath this line. Slope of -1, x and y, intercept of s. X and y are uniform on 0 to 1. I'm assuming they're independent, so their joint PDF is going to be the product of their individual PDFs, which is 1 between 0 and 1. And the product will also be 1 over a square that intersects the x and y axes at 1. Now, S could be as large as 2, or very close to 2. But x and y individually are still varying between 0 and 1. So this square is where the joint PDF is positive and has a value of 1, in fact, 1 times 1. But to integrate over this region, well, when I have to think about cases, because when S is less than 1, it's a triangle. If S is bigger than 1, if this y-intercept is bigger than 1, it's not a triangle, the region under there and still in the red square. It's more complicated. Case 1, S is between 0 and 1. And the integral looks just like the integral for the exponential one, except the integrand is simpler. It's just 1 times 1. Fx of x and Fy of y, when the inputs are between 0 and 1, are both 1, and therefore their product is also 1. That's a 1. Integrate with respect to y first, then x. Integrating 1, of course, is easy. Integrate 1 with respect to y, you get y. Y goes from 0 to s minus x. And then that's going to be integrated with respect to x. I'm going to integrate s minus x with respect to x. Keep in mind that s is a constant, so I get s times x minus 1/2 x squared. X going from 0 to s. That's going to give me s squared minus 1/2 s squared minus 0 minus 0. It all simplifies to 1/2 s squared, a quadratic function. The PDF of s then is going to be linear. The derivative of this will be just s. If, once again, s is between 0 and 1. Not uniform. The sum is not a uniform distribution. It's linear, though. It's got a slope of 1. What happens in the other case? Case 2. S is between 1 and 2. That's trickier because the graph of that line now looks like this. And the part that I have to integrate over is this part, which is no longer a triangle. Though you could break it up into a rectangle and a trapezoid. Integrate over each piece and add. Or what's probably best is to do 1 minus the integral over this piece. Right? That makes sense? The integral over the entire thing has to be 1. Integral over the green piece plus the integral over the blue piece, it's got to equal 1. So the integral over the green piece is 1 minus the integral over the blue piece. So in this case, that's what's best to do. Think of this as 1 minus, do it in blue here, 1 minus the double integral of 1 times 1, which is 1, dy dx. The hardest part here is the limits of integration. Remember, this green line here has equation y equals s minus x. What are the coordinates of that point? For a fixed s? Well, this is at 1. They are where this line intersects y equals 1. If y is 1, that implies x is s minus 1. That is the first coordinate of this point, s minus 1, and the second coordinate is 1. Make intuitive sense? I mean, if s is close to 1, then s minus 1 is close to 0. If s is close to 2, then s minus 1 is close to 1. What about the coordinates of this point here? 1 comma something. Actually, what should be 1 comma s minus 1 by symmetry. The x coordinate at this point and the y coordinate at that point are the same. Actually, we only really need the x coordinate. For x, it's going from s minus 1 to 1, looking at those two quantities right there. And y, for any such given x, goes from the second coordinate of this point to the second coordinate of that point. The second coordinate of the top point is 1. This is a 1 here. What's the second coordinate of that point? For a fixed x, it's s minus x, right? Because the green line has equation y equals s minus x. Oh, this doesn't look so simple. But it's doable. Hang with me. So it's 1 minus the integral from s minus 1 to 1. The integral and the integral is with respect to y. We get y going from s minus x to 1. And then that gets integrated with respect to x. Plug in the numbers. 1 minus, in parentheses, s minus x is going to be 1 minus x, s plus x. That's getting integrated with respect to x. Getting close. This becomes 1 minus, in parentheses, integrate with respect to x. Get this. Plug in the numbers. Be really careful not to make a mistake. Replace s with 1 there, x with 1, sorry, this is an x. X with 1 there, get just 1 minus s. Replace x with 1 there, get 1/2. Subtract 1 minus s times s minus 1. And then add 1/2 s minus 1 squared. Distribute the minus sign through in a couple different spots here. There's one to go through here. There's one to go through here. Oh boy. Let's see. 1 plus 1/2 is 3/2. 1 minus 3/2 is negative 1/2. Minus s is plus s. Then here's the trickiest part. Let's see. That minus sign makes that the minus sign plus. 1 minus s times s minus 1 could be thought of as negative s minus 1 squared. Right? I got 3 minus signs going on there. I got the minus sign that came here through there, making that a plus sign. And then the minus sign through there becomes then a minus sign effectively. But then, oh, wait a minute. So did I get it wrong? Oh boy. Mathematica. I want to make sure I get this right. Mathematica. Okay. We had students begging for Mathematica here. So let's see. It's just too easy to make a mistake here. Oh no, what's it doing? 1 minus in parentheses. What is it doing? Okay, stop it. It's like, I don't want to do it. 1 minus in parentheses, 1 minus s. I'm just going to type the whole thing here. Plus 1/2, not underscore. Minus in parentheses, 1 minus s times s minus 1 plus 1/2 s minus 1 squared, and hopefully I didn't make a typo. Okay, expand. Oh, okay. So let's, I might have made a mistake here. Is that a minus sign or a plus sign? Is this a plus sign or a minus sign? I'm not sure. But Mathematica is saying the final answer is negative 1/2 s squared plus 2s minus 1. Maybe mistakes here. Mistakes, question mark, here and here. Okay. Trusting Mathematica, this being the final answer. What does that mean about little f sub s of s being the derivative of capital S sub s of s? It must be negative s plus 2. Hey, that's a different formula than before. Well, that's because it's a different case. First case, s was between 0 and 1. Now s is between 1 and 2. It's got a different formula. What does the total graph look like? What's the final overall formula for little f of s or sub s of s? Piecewise formula, it's little s if s is between 0 and 1, and little s plus 2 if s is between 1 and 2. And what does the graph of that look like? It looks like a triangle. And it's continuous. Yeah, they both equal 1 when s is 1. The uniform distribution over a 0, 1, when you add them independently, has become a triangular distribution for their sum. And this is correct. This is right. And yes, that does look more normal than a uniform distribution does. They're both symmetric, but the triangular one tails off. It's a little bit more like a bell-shaped curve. I mean, it's got a point there at the top, but it's a little bit more like a bell-shaped curve. Central limit theorem. But I've never said it that way before this year. I've never said it as central limit theorem. But I guess I've started a new trend. It's the central limit theorem. Do we believe this? Let's use some simulation. Spreadsheet equals RAND. Uniform on 0, 1. How many samples should I do here? What sample size? How about sample size 25 here? Copy and paste that over to the next column. Columns A and B are both 25 observed values of X and Y individually. Now let's add them. Spreadsheet. Make me a graph. Insert. Chart. Not that chart. Histogram. Doesn't look like a triangle, not really. Never fear. I'll just simulate again. If the first simulation doesn't work, try a second simulation. That didn't work either. Okay, yeah, maybe I need to customize it more. Maybe I need bigger sample sizes. Okay, this is not working. A little bit better. Keep doing it. Okay, this sample size is just too small. There we go. Of course, that was cheating, right? Okay. Do it over and over until you get the right experiment to prove what you want to prove. I've just done some bad science here. That's a bad way to do things. But I do believe my theory, and I just believe that those were not big enough sample sizes to, and maybe it was bad choices for the histogram categories. Okay, if I'd had bigger sample sizes, I think it would have worked the first time. The distribution of the sum is triangular. What about the distribution of the average? Huh? Average? X plus Y is the sum. What's the distribution of their average? X plus Y over 2. And if you've had stats before, you know we call this X bar. Although we usually don't have a Y there. We usually have an X1 plus X2 over 2. Is X bar, that's a stat symbol. That's chapter 6. That's a statistic. What's a statistic? We'll come to that in a minute here. By the way, what I'm saying now is introducing chapter 6, and it is part of reviewing for the exam. This is called a sample mean. If X and Y are independent random variables from the same distribution, this is called a random sample of size 2. You should have read about this. In general, we have random samples of size n. N is called the sample size. This is a random sample of size 2 from if they're independent random variables from the same distribution. The distribution itself, the uniform distribution in this case, is thought of as being the population distribution. There's a random sample, independent random variables with that same population distribution, and there's a statistic, an expression, a random variable that can be found from the random sample. This is all in the reading at the beginning of chapter 6. What's its distribution? Well, we figured out the distribution of the sum. What if you divide it by 2? Could I use the CDF method again? Well, this is weird. Capital F sub X bar of little x bar. Oops, should be a less than or equal to. Less than or equal to little x bar. Yeah, I guess according to what we did before, at least in this uniform case, we're going to get the CDF of the sum evaluated not at S, but at 2x bar. And that'll mean the PDF of x bar will be the derivative of the CDF of x bar, and that'll be related to the derivative of the CDF of S using the chain rule to get an extra factor of 2. That'll be 2 times the PDF of S evaluated at 2x bar. What in the world? Think of the X, capital X bar, as being the random variable, the statistic I called it, and the little x bar is just being a number. The PDF of the sum looked like this triangle over the interval from 0 to 2 with this formula up here. If I use that same formula here, I'll get 2 times 2x bar and 2 times negative 2x bar plus 2. The first 2 comes from multiplying by 2. The second 2 comes from multiplying the input by 2. 2x bars between 0 and 1 here. 2x bars like the S. And 2x bars between 1 and 2 here, which simplifies to 4x bar and negative 4x bar plus 4. The first inequality is equivalent to saying x bars between 0 and 1/2, and the second one's equivalent to saying x bars between 1/2 and 1. And the graph of this, it also looks like a triangle, but now from 0 to 1, this is a half here, And this is actually 2 there. It's a transformation of the previous graph, squished in the horizontal direction and stretched in the vertical direction. The area under it's still 1. It's still a PDF. That's the distribution of the sample mean. I know I went quick there. So how is this related to what could be on the exam? You want to understand these basic concepts in chapter 6 on the exam. The word population could mean various things. It could mean an actual population of people. It could mean an actual population group of companies in the country, an actual population of machine parts that your company manufactures. It could be an actual population in the usual sense of the word. It could be a population in a more abstract sense, as being effectively a distribution, uniform distribution in this example. The word sample could mean a sample of people. Pick a and put the word random in there. It could be a random sample of people. Like I could take a random sample of people from this class. How? I could put all your names in a hat, mix up the hat. It's the old-fashioned way to do it. Close my eyes, pick out a couple names. There's a random sample of people. I could have a random sample of companies. I could have a random sample of parts that have been manufactured by my company. And I could test them. And maybe I'm trying to know some characteristic, like what's the average height of people in this class, for example. I might want to know that without measuring everybody's height. Or a random sample could be more abstract. It could be a couple, 2 or more independent random variables from the same distribution. Like these 2 random variables is a sample of size 2. They're independent and they're from the same distribution. That's called a random sample in a more abstract sense, which is actually what our book emphasizes, is the abstract sense. And there's a statistic. There is a random variable I can compute from my random sample. I can write a formula for it. X bar is x1, x plus y over 2. It's their average. It's called the sample mean. It's a statistic. It's a random variable created from a random sample by some formula or some rule, some function of a random sample, really. Now, you could observe values of x and y. X is 0.27 and y is 0.49, and get an observed value for their sample mean. And you'd use lowercase letters in that case. But it is important, and the main thing I want you to know conceptually, maybe for true-false questions, maybe for multiple choice questions on the exam, is that this is really a random variable. It's got a distribution. That's what I was showing you here. I was showing you what the distribution of the sum was. And here I was showing you how to figure out the distribution of the mean. And in both cases, they're triangular, but they're different triangular distributions. Again, in the book, in the reading, a random sample in general has size n random variables, independent random variables from the same distribution. And a statistic is a function of a random variable. And for the sample mean, if you have n such random variables, here's its formula. Add up those n random variables and divide by n. There are other statistics mentioned in chapter, oops, I forgot my bar, very important. There are other statistics mentioned at the end of chapter 6. I'm not going to test you on them in exam 2. I want you to know this is the sample mean. Other ones mentioned include the sample variance and sample standard deviation. And there's also the idea of a median. And there's a population median and a sample median. Focus on the sample mean. Okay. It's a random variable. It's got a distribution. In the general case with n, a random sample size n, you'd have to think about it to compute this distribution. You'd have to think about an n-dimensional integral, not a double integral, not a triple integral, but an n-dimensional integral where n could be 1,000,000. Really? It's not as hard as it sounds. And you'd want to verify things like this. And the central limit theorem says when n is large, this is approximately normal. And it doesn't matter what the original population distribution is.